Kummersdorf Proving Grounds, Germany, July 1944, 0800 hours. An Oberingenieur Heinrich Kniekamp stands in the cavernous testing hall of the Waffenamp's most secure facility, staring at something that should not exist according to everything German engineering doctrine holds sacred. Before him sits a captured American M4 Sherman tank, its olive-drab paint scarred by combat, brought back from France at considerable effort after being abandoned by its crew near Caen. Kniekamp, one of Germany's most respected tank designers, responsible for innovations in the Panther and Tiger programs, has been ordered to conduct a complete technical analysis of this enemy vehicle, to understand how the Americans are producing tanks in such staggering numbers, and to identify any technologies worth copying. What he discovers over the next 6 weeks will shake his fundamental understanding of engineering philosophy and force him to confront an uncomfortable truth. The Americans have won the tank war, not through superior engineering in the German sense, but through a completely different conception of what engineering excellence actually means. The German engineers approach the Sherman with a mixture of professional curiosity and barely concealed disdain, because German tankers have been reporting for months that American tanks are inferior to German designs in almost every measurable combat parameter. The Sherman's 75mm gun cannot penetrate a Panther's frontal armour at combat ranges. Its own armour is inadequate against German 75mm and 88mm guns, and its height makes it an easy target. German tactical reports describe Shermans as death traps that burn easily when penetrated, leading to the dark humour among panzer crews who call them Tommy Cookers or Ronsons, after the cigarette lighter advertised to light every time. Kniekamp himself has read these reports and expects to find an inferior design, perhaps something rushed into production without proper development, certainly nothing that could challenge German technical superiority. The shock begins the moment his team starts their examination. Hauptmann Werner Osenberg, a mechanical engineer serving as Kniepkamp's deputy, supervises the initial disassembly and immediately notices something strange about the Sherman's construction. The tank uses large cast sections for both the hull and turret, components that would be extraordinarily difficult to produce in Germany, where casting technology has never achieved this level of sophistication. German tanks rely primarily on welded flat plates or smaller castings joined together, because German foundries cannot reliably produce single-piece castings of this size with consistent quality. Osenberg measures the turret casting and confirms it weighs over 5,000 kilograms, the single piece of homogeneous armour steel formed in one pour with no weak joints or seams. The technical implications are staggering, because this means American foundries can produce in hours what would take German factories days or weeks of welding and fitting. The engine removal reveals the next surprise, as the entire power plant comes out as a single unit in less than 30 minutes, using the Sherman's built-in crane system. Kniekamp watches in amazement as 4 mechanics accomplish what would require a full day and a dozen men on a German tank. The Continental R975 radial aircraft engine sits before them, a 9-cylinder, air-cooled radial that looks absurdly simple compared to the complex liquid-cooled engines in German tanks. Lieutenant Franz Bauer, a propulsion specialist, begins his examination expecting to find crude workmanship, but instead discovers something that makes him call Kniekamp over immediately. Every bolt, every fitting, every component is standardized and interchangeable, not just within this engine, but across the entire American automotive industry. The spark plugs are standard commercial aviation parts available from any American aircraft parts supplier. The magnetos are identical to those used on civilian aircraft. Even the mounting bolts match standard industrial specifications. Bauer pulls out a captured American maintenance manual translated by German intelligence and demonstrates something that seems impossible to the German engineers. According to the manual, a Sherman crew can replace the entire engine in the field in under 4 hours using only standard tools and the tank's own equipment. A German tank crew attempting the same task on a Panther would need several days, specialized tools, and probably a recovery vehicle to transport the tank to a rear area workshop. The Americans have designed their tank not for engineering perfection, but for maintainability by ordinary soldiers under combat conditions. This represents a completely foreign design philosophy to engineers trained in the German tradition, where complexity and precision are marks of quality. The transmission and final drive units provide the next revelation, as these components, which are chronic failure points on German tanks, appear almost comically overbuilt on the Sherman. Obergefreiter Karl Hoffmann, a transmission specialist who has spent hundreds of hours trying to fix the perpetually problematic transmissions in Panthers and Tigers, cannot believe what he finds. The Sherman's transmission is a simple 5-speed manual with a controlled differential steering system using commercial truck components manufactured to automotive industry standards rather than custom precision parts. Hoffmann tests the gear meshes and clearances, expecting to find the loose tolerances that would indicate crude manufacturing, but instead discovers that while the tolerances are indeed wider than German specifications, the components show almost no wear, despite the tank having clearly seen extended combat use. The testing crew retrieves the tank's maintenance logs from inside the turret, documents that survived because American crews keep meticulous records. The logs show this particular Sherman, serial number 3055745, has operated for 847 hours since leaving the factory in Detroit, Michigan. It has crossed the Atlantic, participated in the Normandy invasion, fought through the Bocage country, and was finally disabled not by mechanical failure, but by a hit from a German anti-tank gun that penetrated the thinner side armour. In those 847 hours, according to the logs, the crew performed routine maintenance, changed oil and filters, replaced worn tracks, but never experienced a single major mechanical failure. Hoffmann, who regularly deals with Panthers that break down after 150 hours and require complete transmission replacements, finds this almost impossible to believe. Kniepkamp orders a complete metallurgical analysis of the Sherman's armour, sending samples to the Waffenamt's materials laboratory in Berlin for testing. The results that come back 2 weeks later only deepen his confusion. The armour is homogeneous rolled steel, nothing exotic, with hardness levels that are actually lower than German face-hardened armour specifications. According to German armour theory, this should make the Sherman's armour inferior, easier to penetrate, and more prone to catastrophic failure. Yet American crews are surviving hits that would kill everyone in the German tank, and battlefield reports indicate that Shermans which are penetrated often do not burn immediately, giving crews time to escape. The laboratory director, Professor Dr. Ernst Weinstein, includes a note with his report expressing puzzlement at American armour philosophy, suggesting that perhaps the Americans are prioritising crew survivability over maximum armour efficiency. The interior layout of the Sherman provides still more surprises as the German engineers climb inside to examine the crew positions. Everything is spacious compared to German tanks where crews work in cramped conditions, surrounded by sharp edges and hard surfaces. The Sherman's interior has rubber padding on surfaces where crew members might hit their heads. The seats are adjustable, and there is actually room to move around when wearing winter clothing. Lieutenant Wolfgang Bittrich, himself a former panzer commander who was wounded and transferred to technical duties, sits in the commander's position and experiences something he never had in German tanks. He can actually see outside the vehicle using a combination of periscopes and vision blocks that provide a panoramic view. And when he rotates the turret using the powered traverse system, it moves smoothly and quickly without the jerking and grinding that characterizes German electric traverse systems. The gun stabilization system becomes a particular source of fascination and frustration for the German engineers, because it represents technology that Germany attempted to develop but never successfully implemented. The Sherman's gyro stabilizer keeps the gun relatively steady while the tank is moving, allowing for reasonably accurate fire on the move, something German tanks simply cannot do. Oberingenieur Peter Schumann, the Waffenamt specialist in fire control systems, spends 3 days examining the stabilizer mechanism and comes to a reluctant conclusion. The American system is not particularly sophisticated by German standards. It uses relatively simple gyroscopes and hydraulic actuators, but it works reliably in field conditions. German experiments with stabilization systems have all failed because German engineers insisted on precision and complexity, trying to achieve perfect stabilization rather than the good enough stabilization that the Americans accept. The electrical system reveals another fundamental difference in design philosophy, as every electrical component in the Sherman is waterproofed, overbuilt, and designed for field replacement. The 24-volt system uses commercial automotive components. The wiring is color-coded and clearly labeled, and the circuit breakers are accessible and resettable without tools. Hauptmann-Osenberg compares this to the electrical systems in German tanks, where complex wiring harnesses require specialized knowledge to repair, components are custom-made and difficult to replace, and waterproofing is often inadequate. He calculates that the Sherman's electrical system probably costs a fraction of what German systems cost to produce, yet appears to be significantly more reliable in actual use. The tracks and suspension system provide yet another example of American design priorities, as the vertical volute spring suspension is simple, robust, and easy to maintain. Each bogie wheel assembly can be replaced independently without affecting the others. The springs are massive coils that can absorb tremendous punishment, and the track blocks, while made of rubber-covered steel, are designed to be field replaceable by the crew. Hoffman, examining the suspension, notes that German interleaved road wheel systems are theoretically superior in ride quality and weight distribution, but a single damaged inner road wheel on a German tank can require removing multiple outer wheels to access it, a task that can take an entire day in field conditions. The Sherman suspension can be repaired much faster, despite being less sophisticated. The most shocking discovery comes when the engineering team calculates the manufacturing time and cost for the Sherman compared to German tanks. Using German industrial methods and accounting for the complexity of various systems, Kniepkamp estimates that this M4 probably required somewhere between 7,000 to 10,000 man-hours to produce, and cost the Americans perhaps $50,000 to $60,000. A German Panther requires over 55,000 man-hours to produce, and costs significantly more in resources and labour. The Americans are producing tanks 6 times faster than Germany can produce Panthers, and they are doing it with a vehicle that, despite being inferior in direct combat capability, is actually reaching the battlefield in working condition and staying operational far longer. Oberst Dieter Kramer, the Waffenamt officer overseeing the evaluation, receives Kniepkamp's preliminary report and immediately recognises its implications. The Americans have not designed a superior tank in the traditional sense, they have designed a superior production system. Every aspect of the Sherman reflects choices made to maximise production speed, minimise manufacturing complexity, ensure field maintainability, and allow for mass training of crews and mechanics. Where German engineers optimise for performance and technical elegance, American engineers optimise for quantity, reliability, and logistical sustainability. Kramer realises with sinking dread that this is a war Germany cannot win, because the Reich is trying to outproduce America with artisanal methods against industrial mass production. The testing program continues with actually running the captured Sherman on Kummersdorf's test tracks, and this is where the American reliability advantage becomes undeniable. The tank, despite having been in combat, abandoned in the field, recovered by Germans, and transported across occupied France, starts immediately and runs smoothly. The engine, which should be worn out after 847 hours of operation, shows consistent oil pressure, maintains proper temperatures, and develops full power. The transmission shifts through all gears, the steering responds predictably, and the tracks, while worn, show no signs of the chronic problems that plague German track designs. After a week of daily test runs accumulating another 40 hours of operation, the Sherman still runs perfectly with no mechanical issues whatsoever. Lieutenant Bauer, watching the Sherman complete yet another trouble-free test run, makes an observation that captures the entire German dilemma. He notes that this particular American tank, built by men and women in Detroit who probably had no previous experience building military equipment, using mass production methods with relatively wide tolerances and commercial components, is more reliable than German tanks built by skilled craftsmen using precision manufacturing in specialized factories. The realization is deeply troubling for German engineering pride, suggesting that perhaps precision and complexity are not actually virtues in military equipment that must operate under combat conditions with minimal maintenance. The report that Kniepkamp finally submits to the Waffenamt in August 1944 is remarkably honest in its assessment, while still attempting to maintain German technical dignity. The document acknowledges that while the Sherman is inferior to German tanks in firepower and armour protection, it possesses significant advantages in mechanical reliability, ease of production, maintainability, crew ergonomics, and operational availability. The report specifically notes that American design philosophy accepts lower performance specifications in exchange for guaranteed reliability and ease of manufacture, a trade-off that German engineering culture has always rejected. Kniepkamp recommends that Germany consider adopting some American practices, particularly regarding standardization and maintainability, but acknowledges that fundamental changes to German manufacturing methods would be impossible at this stage of the war. The Waffenamt's response to the report demonstrates the inflexibility of German military bureaucracy, because rather than taking the lessons to heart, senior officials essentially dismiss most of Kniepkamp's recommendations. They argue that German engineering superiority remains valid, that the Panther and Tiger are better tanks than the Sherman when they work properly, and that Germany's problems stem from material shortages and bombing damage rather than fundamental design philosophy. The officials note that Germany cannot adopt American mass production methods because the Reich lacks both the industrial capacity and the natural resources that America possesses. This response, while factually accurate regarding resources, misses the deeper point that German tanks are too complex for the industrial capacity Germany actually has. The captured Sherman, after testing is complete, receives German markings and is assigned to Panzerersatzabteilung 100, a training unit that uses captured vehicles. The crews training on this Sherman universally prefer it to the German tanks they will eventually operate in combat, because it is easier to drive, easier to maintain, and far less likely to break down during training exercises. These men understand what the Waffenamt officials refuse to acknowledge, that a reliable tank that actually reaches the battlefield is more valuable than a superior tank that breaks down en route. German mechanics in field workshops become increasingly familiar with captured Shermans as more fall into German hands during the fighting in France and later during the Battle of the Bulge. These mechanics universally admire the American tank's engineering from a practical standpoint, noting that repairs that would take days on German tanks can be completed in hours on Shermans. Some German units specifically request captured Shermans for use as recovery vehicles because their reliable powertrains and robust construction make them ideal for towing disabled German tanks. The irony is not lost on anyone involved that American tanks are recovering German tanks whose superior engineering has caused them to break down. The German use of captured Shermans in combat operations provides its own lessons, because these vehicles, despite being operated by crews trained on German tanks and maintained with whatever parts can be scavenged or fabricated, continue to demonstrate remarkable reliability. Kampfgruppe commanders who have both German and captured American tanks available often prefer to use the Shermans for critical missions where mechanical reliability matters more than firepower, understanding that a Sherman will actually arrive at the objective while a Panther might break down en route. The most telling comparison comes from Oberst Hans-Ulrich Rudel, a Luftwaffe ground attack pilot who destroys hundreds of Soviet tanks during the war and sees both German and American tanks in combat. In his post-war memoirs, Rudel notes that while German tanks are individually superior when they work, American tanks win through sheer numbers and reliability. He describes attacking American armoured columns where destroyed or disabled Shermans are quickly recovered and repaired, often returning to combat within days, while German tanks that break down frequently must be destroyed by their own crews to prevent capture because recovery and repair capabilities are inadequate. The broader implications of the Sherman analysis remain relevant long after the specific report is filed, because the fundamental conflict between German and American engineering philosophies represents different answers to the same question: what is the purpose of military equipment? German engineers, trained in a culture that values technical excellence and precision craftsmanship, design weapons that represent the pinnacle of what is theoretically possible. American engineers, working in a culture of mass production and practical problem solving, design weapons that are good enough to do the job while being easy to build, maintain, and operate in large numbers by minimally trained personnel. The tragedy for Germany is that by the time the Waffenamt analyses the Sherman in 1944, the war is already lost, and no amount of engineering wisdom can change the outcome. Even if Germany had adopted American methods in 1944, the industrial capacity simply does not exist to implement them. The Allies are producing tanks, aircraft and ships at rates that dwarf German production, and American equipment, while individually less sophisticated than German counterparts, arrives at the front in working condition, stays operational longer, and can be repaired more easily when damaged. The Sherman analysis thus becomes an epitaph for German engineering hubris, a detailed documentation of how technical superiority, without industrial capacity, is worthless in modern industrial warfare. Kniepkamp himself survives the war and works in post-war tank development, first for the Soviet Union and later for West Germany. In interviews conducted in the 1960s, he reflects on the Sherman analysis and admits that the American approach to tank design was ultimately correct for the conditions of World War II. He notes that German engineers were designing tanks for wars they imagined, where individual technical superiority could overcome numerical disadvantage, while American engineers were designing tanks for the war they were actually fighting, where production volume, operational reliability, and logistical sustainability determined victory. This difference in perspective, Kniepkamp suggests, explains why Germany lost the tank war despite producing some of the most impressive armoured vehicles ever built. The legacy of the Sherman, understood properly through the German analysis, is not that it was a great tank in the traditional sense, but that it was a greatly successful tank that achieved exactly what it was designed to achieve. It could be produced in enormous numbers, it could be operated by crews with minimal training, it could be maintained under field conditions with limited tools and parts, and it stayed operational long enough to accomplish its missions. These characteristics, which German engineers initially dismissed as evidence of inferior design, proved to be exactly the characteristics that win industrial wars. Modern military procurement debates often replay the same tensions that the German Sherman analysis exposed, because the fundamental questions remain unchanged. Should military equipment be optimized for maximum technical performance or for ease of production and maintenance? Should designs push the boundaries of what is possible or focus on what is practical and achievable with available resources? Should crews be expected to adapt to complex equipment, or should equipment be designed around the limitations of average crews? The Sherman represented one set of answers to these questions, answers that proved effective in World War II and influenced American military equipment design for decades afterward. The German engineers who examined that captured Sherman in Kummersdorf during the summer of 1944 were looking at more than just an enemy tank. They were confronting the reality that American industrial capitalism, with its emphasis on standardization, mass production, and practical efficiency, could produce military power at a scale and sustainability that German industrial methods could not match. The 850 hours that Sherman had accumulated in combat without a single major mechanical failure represented something that German engineering culture found difficult to accept, that sometimes good enough, produced in quantity, maintained easily, and actually available for combat, is better than perfect, produced in limited numbers, difficult to maintain, and often unavailable due to breakdowns. The story of German engineers analysing the Sherman is ultimately a story about different approaches to solving problems, about how cultural assumptions shape technical decisions, and about the importance of designing for the reality of war rather than for theoretical perfection. That olive-drab tank sitting in the testing hall at Kummersdorf, scarred by combat but still running perfectly, told a story that no German official wanted to hear, but that the mechanics and engineers understood perfectly. America had won the tank war not through better engineering in the German sense, but through smarter engineering, in the only sense that matters during industrial warfare. Engineering that prioritizes getting reliable equipment to the battlefield in overwhelming numbers.